But I did want to kind of just start. I know we rushed a little bit at the end of the last class, so I wanted to take like a minute just to be like, does anyone have any questions? We're kind of moving on to slightly different material. Obviously, we will come back to Lagrangian submanifolds because they're a really important idea. But if anyone had any questions about that or any of the earlier material, I thought I would just pause and see if anything came up. Okay, you outlasted me. Good. There were a couple of questions. People have been putting questions on Notion. Thanks, everybody. It's kind of a slightly different venue that can be useful for different things. But one note that I thought was important enough that I wrote it down. I didn't say this last time, but when I talked about symplectic vector spaces, I meant finite dimensional vector spaces. I mean, obviously, like, it is interesting to think about infinite dimensional symplectic vector spaces, but like you have to be more careful about what non-degenerate means because infinite dimensional vector spaces aren't isomorphic to their duals. There's sort of various issues there. I'm only going to be talking about finite dimensional ones, right? We want to really think about them as manifolds, and sort of symplectic vector spaces that interest us are usually tangent spaces to finite dimensional manifolds, so everything's going to be finite dimensional. So for example, like that theorem about having a basis, right, that where the form has a particularly nice form, that wouldn't work in infinite dimensions. You would at least have to be much more careful about what you were doing because it uses induction on the dimension. This is the kind of thing that could get you into trouble. All right. So now that we've covered that, I wanted to kind of get into our topic for today, which is, all right, we've talked about specific examples of symplectic manifolds. Basically, the only real one we've discussed is cotangent bundles. And that's a very useful, important example, but it's also pretty specific. And whenever you have a structure like this, you can kind of come at it from the other end of thinking, okay, I'm going to fix what my underlying manifold is, and I'm going to think about what the space of all symplectic structures on that manifold looks like. I mean, obviously, that's a very difficult question. We're not going to get super deep into it, but there are a few basic facts about that that are very useful to know and help us with kind of understanding what symplectic manifolds look like going forward. So this is kind of our central question. Given a smooth manifold, what are the possible different symplectic structures on it? Well, if M is odd dimensional, there are no symplectic structures. That's easy. If the dimension is 2, then the symplectic structure is the same thing as a volume form. So a non-degenerate 2 form on a 2-dimensional manifold is what's called a volume form. So one of those exists if and only if the 2 manifold is orientable. That's one way of defining what orientable means. And any 2 choices are the same up to multiplication by a non-vanishing function. So that provides us with another interesting class of examples of symplectic manifolds, but it's also a little boring, right? Volume forms on 2 manifolds, we kind of knew about those before. So what about higher dimensions? Well, that's a lot harder. And of course, there's one hard part, which is just, does a symplectic structure exist? That's a like hard and deep question. I'm going to mostly put that to the side and kind of only think about, well, what if we had a manifold and we found 2 symplectic structures on them? How could we compare them? Well, as soon as you do that, you run into kind of an issue, which is I said, fix the underlying manifold, think about the symplectic structures on them. And you could kind of mean 2 things by that. You could mean, here I have a literal manifold, a set of points with a topology, and this extra structure of an atlas. What are the different 2 forms on it, which are symplectic? That's one question. But what if I actually was only interested in that underlying manifold up to diffeomorphism, right? What if I said, okay, 4 sphere isn't a good example because that doesn't have a symplectic form, but a 4 torus, right? So the product of 4 circles. That has a symplectic form by thinking of it as a quotient of R4, or thinking of it as the product of 2 surfaces with symplectic forms on them. But, you know, not all of the symplectic forms on that guy are going to come from, here's a surface with a volume form, here's a surface with a volume form. Take a product. What about other ones? What do they look like? But if you're thinking of your surface or your manifold, since we're thinking about higher dimensional things, only up to diffeomorphism, you have to account for the fact that there are a lot of self-diffeomorphisms of a given manifold. The diffeomorphism group of a manifold is really big. So there are going to be a lot of symplectic forms which are different as literal 2 forms, but which give symplectomorphic symplectic manifolds. And the term I used here is very floppy, right? Being a manifold, it's a mostly topological structure. It's sort of somewhere right on the boundary being topological and analytic. So it can stretch a lot. And so given any self-diffeomorphism of your manifold, you can take one symplectic form and pull it back by all those different diffeomorphisms. And you're going to get a huge number of 2 forms, which are kind of literally different, thought of as 2 forms on the manifold, but they're all going to be symplectomorphic. So if you're asking, like, what are the different symplectic structures up to symplectomorphism, there are going to be many fewer of them. All right, if I'm going to stop using words like floppy, I have to actually write some definitions. So the book starts this chapter, I think it's chapter 6, with kind of this list of 4 different notions of equivalence you might want for symplectic forms. So one of them we've talked about before, symplectomorphism. That just means I have a symplectic form omega 1, I have a symplectic form omega 0, I pull back omega 1 by some diffeomorphism, the result is omega 0. Another one that's sort of stronger, that's less likely to hold, but it's kind of easier to understand when it happens and when it doesn't, is what's they call strong isotopy. So the kind of short phrase I would put on this is it's symplectomorphic, but it's via a diffeomorphism that's in the connected component of the identity in the group of diffeomorphisms. So it's by a diffeomorphism that I can connect to the identity via a path. And this is what in differential geometry we would call a flow, a path of diffeomorphisms starting at the identity and going somewhere else. So certainly not all diffeomorphisms of a manifold to itself come this way, but a lot of them do. So still a lot of rich possibilities, and they're a bit easier to control because they can be connected back to the identity by a path. All right, and then finally, there's a notion which is not obviously stronger or weaker than symplectomorphism, which is there's a path of symplectic forms joining the 2 symplectic forms of interest to you, omega 0 and omega 1. So a path omega t from 0 to 1, such that the de Rham cohomology class of this is constant. Some people had expressed a little discomfort with the idea of de Rham cohomology, so let me just write this out in a slightly different way. This means that the difference between omega t and omega 0 is the exterior derivative of a 1 form. It's exact. And this would be for all t. And we'll see in a minute why this is a useful notion to include, right? Obviously, you could also change what the cohomology class is, have it so that this difference is not the exterior derivative of a 1 form. But then life will be much harder. In particular, to some people this might be obvious, to some people this might be very surprising. If two forms are strongly isotopic, they will have the same cohomology class. Basically because it's like there's a homotopy between them. So this is explained in a little more detail in the book. I'm not going to say it right now, but strong isotopy cannot change the cohomology class of a form. So if you're going to have two forms that are related by strong isotopy, they have to have an isotopy between them, given by, let me actually write this out. So strong iso implies that you're symplectomorphic, of course, but it also implies that you're isotopic, because looking at the pullbacks by rho t of omega 1, is that what I want? Yes. Gives me the path. All right, so strong isotopy is this condition that kind of sits in the middle that both implies being symplectomorphic and implies being isotopic. And the thing we're actually going to talk about today is mainly going backwards, starting with an isotopy and constructing a strong isotopy that makes it happen. And so the reason to have this constancy of the cohomology class is if your path doesn't keep the cohomology class constant, it couldn't come from a strong isotopy.
But finding a strong isotopy would involve finding a path of diffeomorphisms that would
yes.
that would pull back. Okay.
Yeah, and I was just about to talk about that.
So sorry.
So
what do you mean by for strong isotopy? What do you mean by diffeomorphism in the connected component of the identity?
Well, I wrote it here. So that means that I have a path of diffeomorphisms. So what does that mean? Think about that. That's a map from my manifold times an interval such that if I fix to the manifold, such that if I fix the coordinate in the interval, so I'm going to write the whole thing as rho. If I fix the coordinate in the interval, I'm going to write rho sub t. I want that to be a diffeomorphism for every t. I want the whole map to be smooth. And I should have also written here, let me add in a tiny bit more space. Should have also written in rho 0 is the identity on here. Okay, so this is these conditions. This is what in, I didn't organize these the right way. So the condition that you have a diffeomorphism at every step and that at time 0 you have the identity, that's the condition of being what's called a flow.
What is where does the term connected component come up here?
Well, I can also think of this as a map from the interval into the space of diffeomorphisms.
Okay.
And at time 0, I'm at the identity, and then I do my path in the space of diffeomorphisms, and I get to rho of 1 at time equals 1, and that gives me the diffeomorphism that relates my two symplectic forms.
Okay, thank you.
So you know, a diffeomorphism of a manifold to itself, you can think of that as like a reparametrization of some kind, right? And this is saying that I get to that reparametrization by starting at the identity and doing a kind of continuous stretching process rather than doing something discrete.
So are the diffeomorphisms, is that, what kind of space are you regarding that as? The space of diffeomorphism?
Topological space.
Okay.
I mean, I could sort of, you can think of it as a kind of infinite dimensional manifold, but I'm just going to say a topological space.
Okay.
You know, there's a usual compact open topology on spaces of maps, etc.
Wait, I have a question. What is the topology on the space of forms, on the space of symplectic forms?
What is the topology on the space of symplectic forms? That's actually a fair question. Yeah, I don't want to sort of say the wrong thing. I don't think this is going to matter. Yeah, so the space of two forms is an infinite dimensional vector space. So now you're making me like slightly concerned about like, oh, what's the right topology to put on that
I mean,
vector
because
space?
like when we
I think
like,
all of them should be fine. You know, so you could say like, you know, pointwise convergence or uniform convergence or whatever kind of convergence of functions you want, right? So I think for now, I'll just say pointwise convergence, which is like the least likely thing to get me in trouble.
okay, because I mean, I asked this because just to be clear that we want when we're pulling back, we want the forms to pull back smoothly also, right?
Yeah. Yeah, I mean the forms are going to deform in a continuous way as well, right? So I'm not too worried about like, yeah, I mean somehow right, if you've thought about like integration and stuff, right, there are all kind of all these different notions of, well, what's the right kind of topology to put on spaces of functions, but I think for us it's not going to matter, so I'll just say pointwise convergence and leave it there. But yes, of course, when I say a path, I certainly don't mean, you know, a kind of arbitrary map from the interval into the space of symplectic forms. That wouldn't be useful. So, yeah, I think pointwise convergence is okay. Yeah, obviously, I am being a little vague about sort of topology here, right? And you might see where, so maybe we'll discuss that in a little more detail later, when this condition will actually turn up and be relevant. I'll also mention that, so in the book, the theorem we're going to discuss, assuming we end up having time, class is going pretty slowly, is this Moser theorem. And Moser theorem. And the book does two versions. So one of which is, they have this kind of version 1, which is when the path from omega 0 to omega 1 is of the form 1 minus t times omega 0 plus t times omega 1. Okay, so in that case, That's going to be well behaved in any kind of topology. Everything is fine. And then they do version 2, which is sort of I have a general path. And you might ask, well, why is it better to use, why bother doing version 2 after version 1? The problem is you might have 2 symplectic forms which are connected by a general path, but the straight line path between them has a point that's degenerate. And so the straight line between them might not be a path in the space of symplectic forms, but some other more complicated path might be. And a little bit, and the straight line path, it sort of helps us to avoid your question, and relatedly kind of makes the proof a little bit easier. All right. Any other questions? So for those of you who are saying, well, wait, you said a smooth manifold has lots of diffeomorphisms to itself. How do I know that? How do I find those? There is sort of a good way to think about this. So any smooth manifold has a lot of vector fields. And the way to see this is, of course, Rn has lots of smooth vector fields, an infinite dimensional vector space of them. And then for any manifold, you can put an open cover on it and then use partitions of unity to stitch together vector fields on each of the separate open sets in the cover. So there's a big, big infinite dimensional space of vector fields on my manifold. And then given a vector field, and I can even strengthen this a little bit to make a time-dependent vector field. So I have vector fields Vt for time ranging from 0 to 1. Then probably that will be the derivative of a flow. So like I said before, a map from m times r to m, or maybe a subset of r, some interval inside r, such that the derivative of my flow is the vector field. Now you have to be a little bit careful about what you mean by that. So I drew a picture here. This means that if I fix a point in my manifold and I look at how it changes as I change my variable t and r, so I can think of that as a path in my manifold. And of course, a path in a manifold has velocity vectors. And what I always want is that at my point at time t, so this is at time t, my velocity vector agrees with the vector field Vt, but of course it has to be at the right point in my manifold. So the velocity vector is, it comes from the vector field Vt, but it's Vt evaluated at the correct point. So this is actually an ODE. That's an ordinary differential equation, since the only thing I'm taking derivative with respect to is time. All right, so there's this kind of standard result from analysis that, or you could say the theory of ODEs, that for a fixed point in my manifold, there's, and any open subset, there's some interval 0 to epsilon where the flow exists on that neighborhood. I definitely don't want to get bogged down in analytical stuff, but this is something we have to be a little bit careful about. Mainly, this means we have to insert compactness assumptions. So if my manifold is compact, then actually I'll be okay. A flow will exist for all time. But if I'm not compact, I can run into trouble. All right. So let me just step back for a moment because I feel like I'm going too fast. If I have a vector field, I can either keep it fixed or I can have it vary with time. I can construct a family of diffeomorphisms, a flow, by taking the integral curves of that time-dependent vector field. Now let's do an example. And this is the example to illustrate why I need to insert some compactness. So I can look at my manifold being R. And I can look at the vector field. This is even going to be time independent. V equals x squared ddx. So that's a perfectly good vector field on R. So what does it mean to try to find the flow that's the derivative of? So a path into R, a function, real valued function, is a integral curve of this ODE if, well, the velocity vector at a given point is the vector at a given time is the vector field V evaluated at that time. So I can write this out as d gamma dt times ddx is equal to gamma squared times ddx. So I can just get rid of the ddx. I chose coordinates, so I'm getting gamma prime equals gamma squared. And let's solve the initial value problem. So fixing my original point is an initial value problem. Sorry. So let's say, for example, my initial value is omega 0 equals 1. Well, you can check that the solution to that ODE is 1 over 1 minus t. So I'm going to run into a problem here. This is like, it's a sort of weird thing about ODEs, right? That you can have this perfectly nice looking ODE, everything involved is a nice smooth function, but the solution blows up, right? So as I approach time equals 1, I shoot off to infinity. And if you think this through carefully, if you sort of start very far out in R, you're going to go off to infinity even faster. So there's no interval in R where this flow exists on all of R. So if you sort of try to think of this as a diffeomorphism from R to itself, you're going to run into trouble essentially instantly. But that's because R isn't compact. So if you do this on a compact manifold, you'll never run into this issue. So this is mostly to explain why every once in a while I'm going to have to say, like, okay, assume that M is compact here, or I could say, assume that my vector field is compactly supported, which is automatic on a compact manifold. And just keep in mind that something crazy can happen if you allow your manifold to not be compact and allow crazy stuff to happen off at infinity.
Ben,
yes.
Just terminology check. This is the same as when I was taught that it's a complete vector field, right? That's what you want, right?
Yes, that's another way to say it, right? Complete vector field. Okay. Yes.
Is that the same thing as a global flow?
Sorry. Yeah, I mean, a complete vector field is one that induces a global flow that exists for all time.
Thanks.
I think that's right. I would want to, I always hesitate to use terminology that I haven't like checked in the book because different people will use these things differently. But yeah, I believe anybody would say that a complete vector field is one that induces a global flow. Okay. Sure, let me see that. Complete vector field is one that is the derivative of a flow. So another way of saying what I said above, theorem, any smooth vector field on a compact manifold is complete, or even more generally, a compactly supported one. Let me say for all time. All right, and on the other hand, x squared d dx on R is not. So I say this by way of explaining why I can so confidently say, given a symplectic form, I can construct lots of self-diffeomorphisms of the manifold, and I can kind of stretch and squeeze and reparameterize things lots of different ways, because I get a way of doing so for every vector field. And the book kind of doesn't do things in this order, but I think it's worth thinking about, okay, if I have a flow like this, and I use that to move my symplectic form around, by which I mean I look at the pullback of the symplectic form by rho t for every t, and I think about how that symplectic form is changing, what happens? Well, I can take the derivative of omega t, this pullback, and that's going to tell me, okay, what kind of direction is the symplectic form moving in? If I take that derivative at 0, that has a special name. That's what's called the Lie derivative of omega with respect to the vector field v0. And you'll note here I have a v0 here because my vector field might be time dependent. And since I'm evaluating at t equals 0, I'm only finding out something about what my vector field is at time 0. So this is sort of, how does my form change as I go along an integral curve? But I should emphasize here, I'm really using the fact that I have a whole vector field. If I just went along the integral curve, I wouldn't have a canonical way to compare the value of the forms. I have to kind of look at this whole flow as one thing. All right. Now, one of the things you have to be careful about, and it's very confusing, at least it was very confusing to me when I first read this stuff, is there are a lot of places where you have to throw in random pullbacks by t, by these flows. And you'll mostly be able to sort out where these should go if you just think about kind of what point you're evaluating things at. But I think it's worth kind of thinking carefully about what happens when I take the derivative of this omega t. So the problem is I can't just take my flow and reparameterize it. So I could potentially do that, fix some s, and make this definition, sigma t is equal to rho of t plus s. but that isn't a flow because S of 0 isn't the identity. So in order to get this all right, I have to take a different definition of this sigma, define it to be rho of t plus s composed with rho of s inverse. Okay, and that's going to have the property that sigma of 0 is rho of s composed with rho of s inverse, so it's the identity. Now, exactly by what we discussed before, the derivative of sigma of t at t equals 0 is my time-dependent vector field v sub s. Okay, so using this formula up above, but applied to sigma instead, I get that the derivative of omega t with respect to t, but evaluated at s, I can use this equation to rewrite rho of t plus s as sigma t composed with rho of s. When I do pull back the swap order, so my, this should have been ddt in this guy. Sorry about that. So this guy on the inside, that's just rewriting what omega t is using the definition of sigma. Now this pullback by rho of s, that's just constant. That doesn't change with respect to t. Now I'm doing this at t equals 0. And then this guy on the inside, taking the derivative of that and evaluating at 0 by the equation I had up above, that's this Lie derivative with respect to Vs. Okay, so we have this pullback by rho of s that sort of comes from the fact that we have to reparameterize our flow. So it comes from this S inverse here.
Sorry, shouldn't the domain of like sigma t just be m, because the t, like, isn't the t coordinate is normally, like, this factor of r corresponds to the time coordinate, no? And yet you fixed it when you write sigma sub t, or you like.
Okay, so I was probably a little sloppy here about.
I mean, I understand you have some map sigma from m to r, and if you like take a.
So here, s is fixed, t is a variable.
No, sure, I understand. I just mean that, like, I could imagine you could write sigma sub t of m as sigma, like, of m comma t or something, but just with the t in the subscript, and then the fact that the domain also includes a copy of r.
I take your point. I don't have, like.
Yeah, I know these are sort of the conventions, but.
Yeah, like I understand what you mean, but I don't know what I should have written instead.
Yeah, no, okay. I just wanted to make sure I wasn't confused.
Yeah, so I mean, I still want to talk about a map that depends on a variable.
Mm-hmm.
And somehow when you want to answer questions about, like, oh, what does it mean for that to be smooth? I mean, yes, okay. I could just erase this part, and then you would have nothing to complain about.
Well, I liked it better with that part, if I get to choose what I.
Yeah.
Sorry.
So I'm just saying, like, right, what you're complaining about is that kind of maybe wasn't quite the right thing to put there. But I hope the meaning is clear, right? So there's something you can do, which is just change, the sigma, you could take it to just be rho reparameterized doing nothing interesting, And the important point is that's not a flood. And yeah, okay. Hopefully we've been that way with that.
Yes, yes.
Yeah, I just think it's worth seeing where this pullback of my row S is. So for example, if you do question 3 on the homework, it's very easy to kind of forget to put a pullback somewhere and have things not work out, which is, you know, the point of the question. to make you feel in the bones like, oh, okay, that's why I needed to put that pullback there. All right. Now, the kind of key observation behind making all of this go is that there's a formula for this Lie derivative. So I can take the Lie derivative of sigma with respect to this vector field, and this is true for any vector field. And I can write that as the exterior derivative of the contraction of the symplectic form with that vector field. All right, and if I write that in terms of the derivative of omega, I just have to stick in this pullback, and I can actually put the pullback inside the exterior derivative, because exterior derivative and pullback commute. And I just want to remind you, what does this iota mean? Because we had discussed it previously. That means take the symplectic form, put your vector field into the first entry, and think of that as a function of one vector field by putting the other vector field into the second entry. So that's a one form, because it's something that eats one vector field and spits out a number. That one form I can take the exterior derivative of and get a two form. Okay. Now, why is this true? Well, in general, there's this Cartan's magic formula, which is that the Lie derivative of any form with respect to a vector field can be written as in terms of contraction and taking exterior derivative. Those of you who like Durham cohomology, algebraic topology, etc., will note this guy on the right-hand side. That's exactly the formula saying that the Lie derivative is null homotopic. And this contraction with the vector field is actually the homotopy that exhibits it as being homotopic to the zero map. But of course, this formula simplifies a lot because omega is closed, right? So I'm again using this property of being a symplectic form. Everything would fall apart if omega wasn't closed, because I would have a second term showing up in that formula. So I'll just mention this is using the fact that d omega equals 0. It's kind of the key to making all of this work. And I think at least one of the reasons this is worth discussing early on is because it sort of illustrates for you one of the places where this being closed is such a key property. Okay. I'll just mention, so this also shows us that this thing I was saying about the cohomology class of omega staying constant. So if I look at the cohomology class of omega t, how does that change with respect to time? Well, its derivative is the exterior derivative of something. So that tells you that the cohomology class never changes. And you could actually find something that the difference was the exterior derivative of by integrating these contributions from each individual moment. Maybe I'll actually write that out. using the fundamental theorem of calculus, we find that omega t minus omega 0 is equal to d of the integral from 0 to t, or maybe I should use s instead of t, of rho t star contraction with vt omega vdt. So this is how you see that the cohomology class never changes. All right, so Justin, are you ready to lead the Q&A/break?
Sure, I can do that.
So I will just step out for a moment, and if you have any questions, you can ask Justin, or if you just want to shoot the breeze with him. I'll be back in a couple of minutes.
How are you guys doing?
Good. So just to get a big picture here of what we're doing, like we have just shown that if you have a flow, an isotopy
Yes.
of diffeomorphisms, right, and you look at the that doesn't change the cohomology class of the form that you flow along, right? But what we're trying to do is go the other way, right? To say, like, if you have a path of symplectic forms, we would like to construct a path of diffeomorphisms along which those forms have been pulled, right? I mean, if you have a path of forms such of forms that lie in a single cohomology class, then we have to go backwards and find a path of diffeos, right?
Yeah, I mean, that's a different question, but yeah.
Oh, what is the?
Well, I'm just saying that finding a, as you said, like proving that if you have I wasn't exactly paying attention to what we were doing.
Oh, okay, yeah.
But yeah, I mean, the thing that he proved just a second ago is that if you have a path of diffeomorphisms, it doesn't change the cohomology class. Yeah, so I don't know which theorem that you guys are going to prove.
Gotcha.
Yeah, sorry, I'm moving out of here. I was packing while while Ben was talking.
Justin, I just have, I don't know, I think it's very naive, but I just can't make sense of it right now. So this whole discussion relies on the fact that the vector field can be time dependent, right?
That a vector field can be what?
Time dependent.
Time dependent.
Right? But so far, all the calculations seems to be exactly the same as what normally the time-independent vector field calculations would have been anyway. So is there anything that is essential here that is specific to time-dependent vector fields?
I don't think that I don't think it's very much different.
Yeah, okay. Because apart from maybe saying that maybe the vector field is no longer related to, say, the exponential map, I just don't see why like none of the calculation seems to be very different.
Maybe it's just slightly more general, because then you have more families of diffeomorphisms that you can
use.
Apply this to.
Yeah, I guess, yes.
Like, I guess it's maybe, is it true that this gives you the converse? Like, if you have any path of diffeomorphisms, then you can take the derivative along that path to get a path of vector fields whose flow is that path of diffeomorphisms. Like, if that's, I mean, assuming whatever analytic things you need to make it nice enough to work.
I think locally that's true, right? Because was it a Lindelof-Picard or something? Locally, you can always do this, but it's just that if you don't know anything more, then you can't do more than this.
Yeah, I don't know. I mean, my guess would be that that's probably that fact would be what the reason that we would need time-dependent vector fields. So we could just so we could go backwards from any flow of, from any path of diffeos, not just one that comes from a constant vector field.
Yeah. Right. So
All right.
Ben, they've been asking about why did you need time-dependent vector fields?
Oh, it's exactly this thing I said at the start. About what your path of symplectic forms looks like. So when we get to the proof, we'll see. If you had a path that was just linear like this, then you could use so what's going to happen is basically if you have a constant vector field and you use that to create a flow, then what's going to happen, let me go here. Exactly what this sort of formula ends up telling you is, I think it's right. It's maybe not quite that it's a linear change, but it's exactly that you don't want to just use straight line paths in the space of symplectic forms, because you might be able to get around a degenerate point if you use a path that isn't constant. So we'll see this when we try to do this
but
backwards.
just to be clear, right? When you say constant vector fields, you don't mean like the vector fields are just straight lines, right? Or I'm asking. Like...
No. I mean that the vector field is independent.
Yeah. Okay, cool.
I'm sorry, I haven't really been paying attention to the chat. Okay, it's mostly stuff earlier. Okay. So we're not exactly defining the definition of a path. So the thing I would say, is that at least for my purposes, the kind of condition I want on a path is that the map from the interval times m to m is a smooth map. Right? That's the kind of that's putting a condition of kind of smoothness on how the diffeomorphisms change. All right. But yes, I'm also I'm afraid that this is just something that is a congenital issue of mine, that I'm a little bit sloppy about analytic issues, and generally just avoid situations where I'm going to have to do difficult analysis. Just try to put on enough hypotheses that it's not a concern. All right. So what, let me get back into the swing of things. So we were just noting that this cohomology class wouldn't change. And so, for example, as I said before, symplectic form on a two-manifold is a volume form. And if your two-manifold is a compact, then that volume form has a number attached to it, the volume of the two-manifold, right? And what this argument above is showing you is that that volume is not going to change when you do a strong isotopy. When you use a diffeomorphism to move things around, you're going to stretch out and have less volume in some regions, but that's going to be compensated by having more volume in other regions. So we've actually found an invariant that you can also, if you think for a bit, the volume isn't going to change under any symplectomorphism. So different volumes give you different symplectic forms which are not symplectomorphic. So congrats us. We found an example of a symplectic manifold with different symplectic forms, which we know are not symplectomorphic. And we'll see later that that volume is actually the only thing that distinguishes two different symplectic forms on a surface.
What do you mean by volume? Is it just volume form? Or do you mean
So
something else by volume?
when I have a volume form on a two manifold, I need to actually have fixed an orientation. So if I have a volume form on an oriented two manifold, or some, a symplectic form, so that means a two form, which is non-degenerate at each point, then I can integrate that two form over the two manifold.
Okay,
Because
thanks.
it's compact, I'm going to get an actual number. And that actual number isn't going to change under any symplectomorphism.
Okay.
So, right, if let's say I have a sphere with the standard volume on it, right? Usually people say that means like volume 1, or I can multiply that by some scalar, right? And I will get a different two form, which has a different integral over the whole manifold. So yeah, we can distinguish between at least some symplectic forms at that. All right. What about more generally, right? So that's kind of one example. In particular, I had mentioned this issue at the beginning of, well, what's the relationship between being isotopic, having your symplectic forms joined by a path that keeps the cohomology class constant, versus being strongly isotopic, being related by doing an isotopy. And basically, we can look at this formula. Let's see which formula, this formula, and try to run that backwards. So this formula is about what would happen if you started with the symplectic form, you chose some vector fields that you were going to integrate to a flow. How would the symplectic form change when you pulled back by that flow? But we can do that backwards. We can say, oh, what if we had a path of symplectic forms? We looked at how the symplectic form changed along that path, and we tried to come up with a flow that did that. You sort of look at the formulas, you can make that work. So assume we have an isotopy, so a path in the space of symplectic forms, such that the cohomology class is constant. So if we can find a formula like this, that the derivative of this guy with respect to t is the derivative of, it can be written in this way. So I find a flow with a vector field v that gives me the flow, the derivative of it with respect to time. If I can sort of come up with a formula like this, then that vector field v will tell me what I need to do. It'll tell me the flow. So if I can solve this equation that I haven't read, then I will actually find strong isotopy relating the forms. So how the important takeaway here is how the symplectic form changes can be used to solve for what the vector field is. Now, we're going to have to add some assumptions in order to be able to integrate our vector field to a flow. So we'll want to assume that M is compact. But once we do that, we can find the vector field and we can use the vector field to give us a flow. So good news, this is actually always possible. So if M is a compact manifold and I have two isotopic symplectic forms on it, so symplectic forms that are joined by a path in the space of symplectic forms that keeps the cohomology class constant, then actually these two forms are strongly isotopic. And in particular, they are symplectomorphic. There is a diffeomorphism from M to itself that relates one to the other. So let me talk for a little bit about what this actually means. The way I like to think about this, so when I first encountered this, I don't know, I didn't kind of know what realm to put this theorem in. But since then, I've learned a lot more about kind of deformation theory. So whenever you want to understand kind of the space of any kind of object, one of the kind of basic questions to ask is, well, if I can think of these as like a manifold or something, what would the tangent space of that manifold be? So that's kind of asking, if I have an object, how can I do kind of very small deformations to it? And what this is basically telling us is on a compact manifold, there's only one way to kind of change your symplectic form a little bit in a way that's kind of like, going a little bit down a path, which is to change its cohomology class. And if I do a change that sort of stays in the cohomology class, that actually won't be changing my underlying form up to diffeomorphism. Yeah. Danae.
Yeah. So should I think about strong isotopy as sort of like a homotopical condition, and isotopy as some kind of a cohomological condition? Is that sort of the way to think about these kind of?
I would say that. I would say that right, what we're I don't know that I have a good answer for that. I guess what I would say is, like, if you think about the space of symplectic forms, I'm probably going to get questions now about, like, well, wait, what kind of space is that? But just imagine for now that you kind of think of symplectic up to diffeomorphism as a kind of space. Oh, sorry. Let me collect my thoughts a moment longer. Okay. So, right. If I have a symplectic form, I can look at its class in H2. And that's kind of an interesting invariant of the symplectic form. Now, thinking about things up to strong isotopy instead of up to symplectomorphism has the advantage that I know strong isotopy won't change the cohomology class. And so if I think of the space of symplectic forms up to strong isotopy, then that's going to actually have an actual map to the second cohomology, right? And what this theorem is telling you is on a compact manifold, kind of the only way to change your symplectic form up to strong isotopy is to actually move to a different point in the image of that map. So I think I said this a little bit down below. It tells us that the tangent space to the space of symplectic forms up to strong isotopy is actually the second cohomology class. And so this map to the second cohomology class, it's an isomorphism on tangent spaces. Now, there could still be all kinds of global stuff going on, right? There could be many different components, each one of which is mapping down with the tangent space being an isomorphism. You could even have kind of one component where somehow, like, you go around some loop and you could be getting like a non-trivial covering, or at least I don't know how to rule that out. Sort of read a little bit about it of the literature about spaces of symplectic forms, but that's sort of the way I would think about this, that like one of the basic questions about, you always ask about moduli spaces is what's kind of their local structure? Because it's very hard to think about their global structure, but often you can find out something interesting about the local structure. And this is telling you kind of locally, the space of symplectic forms up to strong isotopy just looks like a little bit of the second cohomology group.
And the fact that it's finite dimensional is pretty, is remarkable in itself.
I agree.
And this would imply also like for a surface that the space of symplectic forms up to strong isotopy is just one dimensional, right? Like could it be, could you have a loop in this space?
I don't think for a surface. In general, I don't see why you couldn't. But I sort of tried to look up like what was known. Definitely, you can have an infinite fiber. You can have infinitely many different components that map down to one particular cohomology class. But I don't know if I saw anything that confirmed it's possible to have a non-trivial covering. But certainly, I don't know how to rule it out. But I agree, it is surprising that the tangent space is finite dimensional. Right, this is one of these things where like sometimes you find out very surprising stuff, even when you ask kind of purely local questions. All right. Any other questions? So yeah, this kind of tells you it's surprisingly hard to deform a symplectic form and get something non-trivial. Oh, right, what I was going to say about surfaces is, right, so the thing that's different about surfaces is because everything's two-dimensional, if you have two symplectic forms with the same orientation, the straight path between them, where you just sort of take the appropriate linear combination, is always going to be non-degenerate. That's always going to be a symplectic form in the middle. So you can sort of use the easy version of Moser's theorem to construct a strong isotopy between them. Whereas in higher dimensions, you can have two non-degenerate things and have some cancellations. But precisely because the space of two forms on the two-dimensional space is one-dimensional, right? There's sort of the non-zero things come in two components, and anything in the two components you can join in a way that doesn't go through zero. All right, cool. So yeah, I did look up enough to confirm that for manifolds of dimension higher than 2, there can be many different connected components. And even infinitely many different connected components. So sort of, yeah, there's definitely more going on than just the symplectic form, but that's the only interesting kind of local information. There are other discrete invariants you can look up. Like later we'll discuss compatible almost complex structures. And actually, so one of the key invariants is there's a notion of a compatible almost complex structure, and you can look at the Chern classes of that almost complex structure. You can get many different possible Chern classes on the same manifold coming out of your different symplectic forms. All right, cool. So yeah, I think we have time to do the proof. I was a little worried it might spill over into next time, but let's at least start discussing it. So if my two symplectic forms, omega 0 and omega 1, are isotopic, then there exists a smooth path between them. Now, I am going to change notation a little bit from what I was talking about before. So what Canis de Silva does is she constructs a flow such that the pullback by rho t, by the flow at time t, of omega t is omega 0. So to put that in kind of the framework we had before, we would move the rho t to the other side. And I could say, oh, I'm starting with omega 0, and I'm applying rho t inverse to it. And that's giving me this whole path, omega t. But the actual calculations work out a little more cleanly if you do it like Hannah de Silva does. So, you know, I'm following her notation in part just because I think it'd be confusing if I did something different from the book. The other thing is somehow the integration step is conceptually easier, right? Here, you know, I had to actually take an integral somewhere. And so if I tried to do it in this start with one symplectic form and hit it with a flow, then I would have to like compare that to my path and check that the derivatives were the same at each time and then integrate. Whereas if I do it the other way around and do it Canis de Silva's way, well, the right-hand side is constant with respect to time. So I just need to show that the left-hand side is constant with respect to time as well, which is just showing that the derivative is 0. All right. Yeah, so if I show that the derivative of the left-hand side is 0, well, that means it's constant. So I get that the pullback of omega t by rho of t is omega 0. Okay, the disadvantage is now I have to do a slightly more complicated calculation. So what happens when I'm pulling back a time-dependent form by a time-dependent flow? This might require a little thinking, but the answer is you use the Leibniz rule. So you differentiate with respect to the flow, treating the form as constant, and you differentiate with respect to the form, treating the flow as constant. So differentiating the form with respect to the flow gives me my first term here. So this is treat form as constant. And I've got a rho t pullback here. And on the other hand, if I treat the flow as constant, then I'll get this term, which is the derivative of the form with this rho t pullback here. So this is treat, treat the flow as constant. All right, and again, we sort of see why this notation that Canis de Silva used is kind of clever and saves us some trouble. Admittedly, I have to pull back by rho of t, but I'm pulling back both of my terms from rho of t. So if I show that that inside is 0 before the pullback, it's 0 after the pullback as well. Okay, so I get that this derivative is 0 if and only if the Lie derivative of my form with respect to Vt is minus the derivative of my path with respect to time. And again, that minus, this has to do with Canis de Silva flows, and my original flow from before are related by taking a minus sign. So that's why this minus sign shows up here. I was initially a little confused about that, but sorted it out myself. All right, and then using Cartan's magic formula, I get that I have to solve the equation. So I have my path of forms, that's fixed from the start. I'm taking its time derivative. That gives me, again, a 2 form. And I want to solve the equation that that's the exterior derivative of a vector field contracted against the symplectic form. And remember, I'm trying to solve for Vt. Okay, so the first part of this is to get rid of my exterior derivative there. Well, by assumption, the cohomology class of omega t is constant. So when I take the time derivative, I'm getting something which is exact by assumption. So this time derivative of omega t, I can write as the derivative of some one form. And this kind of brings us back to questions people had at the beginning. You know, why do I need to assume some kind of continuity for this path? Well, I want this one form to vary continuously. So I'm just going to sort of say there is some real work involved in checking that this omega t can be chosen to vary smoothly in t. Canis de Silva gets a little cagey about this point, and I think exactly the reason she does the version 1 of the Moser theorem is if this derivative is constant, which is what happens if you have just a linear path, then that means I can just pick one form. So if this right-hand side is constant, I can choose this one form mu to be constant, and I don't have to worry about this issue. Now she says some stuff about Meyer-Vietoris. When I was sort of thinking about this, I think actually there's kind of an easier way to do this. So first, check that this is possible for compactly supported forms on Rn. So hopefully at some point in a vector calculus class, you saw this done at some point, because I'm not going to write out the explicit integrals. But this can be done just kind of writing explicit formulas. If you want to, we will, I think, talk about this more next time. You can use the fact that Rn is contractible and use this homotopy operator Q from Canis de Silva. So one way of doing this is just explicitly constructing it from a contraction of Rn down to a point. All right, and then that's sort of step 1. Step 2, do this on charts. Using a partition of unity. I think this should be okay. If not, then you'll have to just accept Canis de Silva kind of waving her hands and saying Meyer-Vietoris. Unfortunately, I don't know, she claims that this is done in McDuff and Solomon, and I looked up McDuff and Solomon, and they don't do it any more explicitly than Canis de Silva. So, c'est la vie. But that, when people were asking earlier about like time dependence, that's sort of where the time dependence comes in, and you have to be careful about it. All right, but taking for granted that we can do that, we then reduce our equation to, we want to solve this. That when I take my symplectic form, so I have a particular one form, and I want to find a vector field such that when I contract it against the symplectic form, I get that one form. And this part is easy. I can do that because the symplectic form is non-degenerate. So the sort of slick way to say this is contraction against a given vector gives me an isomorphism from the tangent space at any point to the cotangent space at the same point, right? That turns a vector into a covector, and non-degeneracy is exactly saying I can get any covector this way from a unique vector. And I'm also using finite dimensionality there, right? I'm using the fact that this is an injective map between vector spaces with the same dimension. All right, so that map is an isomorphism, and so I can explicitly construct V of t from mu of t by using the inverse of that map. And this is a notion we'll want to use a lot later. I was kind of tempted to refer to this V as a Hamiltonian vector field, but that's not really quite right. Since it looks like I'll have a couple of minutes after we're done with the proof, maybe I'll say a tiny bit about that. But this idea that you can turn a one form into a vector field using the symplectic form, that's a very important idea later. Okay, so that tells us what Vt is. And since I assumed from the start that we were on a compact manifold, I can integrate Vt to a flow. And this flow will exactly get us what we need, that the pullback by rho 1 of omega 1 is omega 0. All right, went through that pretty fast. So are there any questions about the proof?
Could you maybe just scroll to the next sort of 5 or 10 lines, or to the next screen, if you have the same screen? Okay, I see. Never mind. I didn't miss as much as I thought.
Okay.
Where is step 3? Or there's no further. Like you don't have to check that you're. I see. Okay. Never mind.
Yeah. Sorry, Sorry, that step 2, that was really kind of just discussing individual subproblems of if I have a family of exact tuples that depend on time, how do I choose of a derivative in a way that's smoothly varies with respect to time, right? This is sort of, I mean, sounds very plausible, but it's not totally obvious how to do it.
Yeah, thank you.
And, somehow the point is exactly what partitions of unity allow you to do is they allow you to take your 2 form and write it as a sum of compactly supported 2 forms, each one of which is supported entirely inside a coordinate chart. And then you can go back to Rn, find an antiderivative on Rn, and because there are explicit formulas for how to do that on Rn, you can make sure it's done in a way that varies smoothly with respect to time, and then you can add those guys back together.
Yeah, okay, thank you.
And I don't know, Kenneth de Silva usually doesn't use partitions of unity very often, so maybe she wasn't thinking about doing it this way, or maybe there's some subtle issue in this proof I didn't notice. I think both of those are reasonable possibilities. But yes, I probably could have divided this into steps. There's sort of one step, which is just set things up, take the derivative, you get this formula. Oops. And then there's step 2, which is take the antiderivative of the right-hand side. So then you get to this formula, and then I guess that would be step 3, is using non-degeneracy of the symplectic form to solve for VT. So I don't know, I find this, I think when I first learned this as a student, I was a little overwhelmed by the whole thing. But the sort of beautiful point in it is that when you vary the symplectic form, that already contains the instructions for how to reparameterize your manifold in such a way to sort of see that all you're doing is reparameterizing things. And we used all the properties of the symplectic form in doing that. We used closed in a key way because we use this Cartan magic formula in this step to go from the Lie derivative to the differential of the contraction. And we also used the non-degeneracy here. So this proof would be impossible if you removed any of those conditions. All right, so we're almost out of time. Are there any other questions about all the stuff we've talked about today? Let me look at the chat. I think I closed my chat window. There's a question quite a while ago about group structure. And no, symplectic forms don't have a group structure because you can't, if you add 2 of them, you might have degeneracies. So there's no obvious kind of group structure. And in fact, right, so one thing we talked about before, one note from before. Which actually, the student who asked this question, I think maybe wasn't in the earlier classes, so they might not have noticed. If M is compact, then actually the class in H2 of the symplectic form must not be 0. So in fact, this map from the space of symplectic forms to the second cohomology, even though it's an isomorphism on tangent spaces, it isn't surjective. And I'll just remind you, the reason for this was that if I look at the nth wedge power, and then I integrate that over the whole manifold, I have to get something non-zero. Because this nth wedge power has to be a volume form. It's a non-vanishing top form, and any exact top form will vanish somewhere because it'll have integral 0 over the whole manifold. So just something worth noting that in fact we definitely, so that sort of shows you that it can't be a group because there can't be a 0 in the space of symplectic forms, right? And in fact, this this property of staying non-degenerate, it's very kind of subtle. So yeah, I think that's all I have to say. Are there any other questions?
Did you decide when the office hours are?
Oh, No, I should think about that. So, I mean, okay, we can always do office hours by appointment. So just anytime you want to talk, feel free to set up an appointment. I think Justin and I had agreed that we would set up an office hours time, and then I think we didn't. So yeah, let me think about that. Yeah. So feel free to email me with your thoughts on office hours. I have to admit, I just didn't have time over the weekend to look at the getting to know you assignments. So maybe looking through those, I will find out what people's office hours thoughts are. But if you had anything to add, feel free to email me, and I will set something preliminary by this evening. Are there any other questions? All right, then I will shut things down for today. Everybody have a good Monday evening and Tuesday, and I will see you guys on Wednesday.